Maddie, and Noah. So make sure, hopefully all of you have found this on YouTube, or if you're tuning in live, okay, but just make sure that you're able to find this later on if you're not watching it current with me, which is based on what other people have told me with the live streams. I definitely recommend watching it after the class is over officially. So if you're trying to watch it now, don't worry about it. Just come back later, so that way whenever it's finished recording, it'll be able to have, it to be a clear viewing, like clear viewing, I guess, show or viewing performance with the video. It runs a lot smoother. Otherwise, it's really glitchy whenever it tries to run. So if you're trying to do it now, just wait and come back in about 45 minutes, and then you can watch the whole video then. Alright, so let's go over your homework. You had application on page 105, application number 1. And then you also had on page 110, you had questions 1 through 5 as well. So let's go through the application number 1 first, page 105, then we'll move over to 105. Alright, so how much heat must be added to 30 grams of solid iron to melting, assuming that iron is already at its melting point? It tells you to use the tables on page 100 and on page 104 to figure these out. So if you want to put that in your textbooks, one of them to look at it on page 100. It talks about heats of fusion in this section. So this is, remember, it's kind of getting into heats of fusion, or trying to talk about how much substance it takes to melt an object. So if you're looking for the application number 1 for water, if you look on that chart and if you look for water, you'll see for this one that it has a heats of fusion for this one. The melting point, it'll tell you is at 0 degrees, that the heat of fusion is 334. But it's asking for this one, you're asking for iron. So let's go look over for iron. So find iron. No, it's okay. The melting point for iron is 1,538 degrees Celsius, which is really hot. But it tells you, okay, the heat of fusion for iron is 247. So that's how much heat you have to put into iron in order to melt 1 gram of it. But you'll notice in this problem, you don't have 1 gram of iron, you have 30 grams of iron. We'll talk about the heat of fusion later on, so if you're sitting there wondering, I didn't do that right, it's okay. So the heat of fusion is 247 joules per gram, but if we don't have 1 gram, we have 30 grams. So what do you do to solve this? Well, hopefully looking at it now, you can kind of tell, oh, okay, I should have multiplied, and that's what you do for this one. So the answer comes out to 7,410 joules, 366. Because of the 0 with the decimal point, 366, 366. So that's the answer for number 1. If you're a little bit confused, it's okay. We'll talk about it more in class as we get into it. Alright, let's look at on page 110 now, questions 1 through 5. In what process is a liquid changed into a solid? Okay, that's the freezing, or that's the process for freezing, whenever it changes from a liquid into a solid. Define heat of fusion. So heat of fusion is the latent heat required to change a given mass of solid into a liquid without changing its temperature. What is the general term for the process by which a liquid changes into a gas? So that's evaporation or vaporization. You might have said that. Evaporation is the one that you want to note for it. What term describes liquids that evaporate quickly? So that is volatile. If it evaporates slowly, that is non-volatile. So volatile is for liquids that evaporate quickly. Non-volatile is for liquids that evaporate slowly. Define boiling point. The boiling point is the temperature at which a substance boils. So at least that's straightforward. Alright, you can go ahead and put that away. Alright, so if you remember on Friday, I told you we were going to have a quiz today, and we're still going to have the quiz today. But rather than me asking just a bunch of random questions to empty chairs, because nobody's here with me, that gets boring and old really, really fast, and that's not super efficient way to do this. So what I'm going to do, and what I'm going to need you to do, that if you're trying to watch it live, and I can see somebody's at least attempting this, so if you're watching this live, what I need you to do is to pause it, because me just asking the questions over and over again doesn't really work very well. So in order to help you out and benefit from this, is I need you to copy down the bold terms and definitions from pages 88 to 99, because remember that's where your quiz is coming from. So this will help you to kind of study and to double check, do you know your terms and definitions? I only need you to do it twice, so I know that copying terms and definitions is not fun and it's boring, and I know it's not nearly as fun as playing review games, but that's the best way to help you to learn them, so that way if you forgot over the weekend of, oh yes, she did mention that, then this will help you to kind of get a quick review. So as you're writing them, don't just speed write them. You want to copy them out as best as you can, but you also want to try to memorize them. So in a lot of cases, writing them out will help you to memorize them. So it's just the bold terms. Now, whenever I say that, I'm not going to wait the 5 to 10 minutes. It should only take you about 5 to 10 minutes to do. So I'm only giving you about 5 to 10 minutes to kind of study them / write them down, because that would be about how much time we have during class in order to go over it. So I'm giving you 5 to 10 minutes to kind of study it on your own and copy those bold terms and definitions to help you learn them, so that way you're using your time properly for it. Now, I'm not going to stand here and wait 5 to 10 minutes because I have things to do. But since you're trying to watch this later, so whoever the one person is that's currently watching this live, you probably want to just come back later, because you're going to lose your 5 to 10 minutes if you try to keep up with me right now, because I'm not going to wait. So if you're trying to watch this live, make sure that you pause the video or come back and go work on some other class's homework and then come back to this. So that way you have your time in order to be able to study and copy your terms and definitions, so that way you can keep going, so that way you're not short-circuiting yourself for it. So again, if you're watching this later on, go ahead and pause the video so that you can copy down the bold terms from 88 to 99. You want to try to do them twice. It should only take you about 5 to 10 minutes though. You don't spend forever on it. So once about 10 minutes has passed, unpause the video and keep going. But like I said, I'm not going to wait. So we're going to go ahead and go over the bold terms that you should have studied. So whoever the one person is, I guess you're skipping your review. Alright. So I'm going to ask the question that's kind of like a review, so that way you can double check your answers over what important terms that you should have marked down and copied as well. So what is conduction? Alright, conduction is the process by which heat flows through materials between objects in direct contact. So contact is whenever is with conduction, so make a note for that one. Alright, who invented the, I lost my train of thought, I'm sorry. Who invented the minor safety lamp? Now this one was not a bold term, but you do need to know it, so we're reviewing everything, not just the bold terms. Alright, so Humphrey Davy, hopefully you need that one. Alright, what type of heat transfer is it whenever it's the transfer through moving fluids, either a gas or a liquid? Alright, hopefully you said convection, and then what do you call those currents whenever you have one of them is rising and one of them is sinking, so you have that flow of the heat? What do we call that type of current? Good job, just convection current. So those two are pretty much the same thing. Alright, what is the last type of heat transfer where it's just light energy? Now this is the only one that can go through an it's the only one that can go through an object without matter, we'll put it that way. Alright, so what do you call that last type of heat transfer whenever it can just go through the vacuum of space? Good job, radiation. So remember, this one is unique because not only is it light energy, but it can also go through the vacuum of space. It doesn't have to go through something. For conduction, you have to go through something to touch it, or you have to go through an object in order to have it be in direct contact, so it's flowing from matter that way. With convection, it's moving with fluid, so that's matter as well. For radiation, it's just going through space, or it can just go through an object. It doesn't have to have matter for it. Alright. What do you call the types of thermoses that are used to store really, really, really cold stuff, like liquid oxygen, liquid hydrogen, or other liquid gases, or in some cases really hot stuff, but typically really cold stuff? What do we call those types of thermoses? Good job, a Dewar flask. Vacuum bottle is another name for it, but Dewar flask is the one that you want to know for it. Alright, there's two different systems of heating homes, and one of them is much more common in America, but technically there's two different systems for it. What type of system is it whenever you're using convection currents with hot water being pumped around throughout the house? Alright, that's the hot water heating system. So make it up for that one. What is the other type of system of heating homes in America? Where this one you're using typically an electric furnace and you're pumping hot air through the house. What do we call that one? Alright, make a note for that. It's forced warm air system. So make a note for those. Now again, if you're listening to these and if you realize, oh, they didn't go quite well, I didn't write down the right things, then make sure that you go back and that you're double checking your answer. If you helped you to write down the term definitions right now, go ahead and write them down for you. Alright, what is the branch of physics that deals with thermal energy, heat, and their relationships to other forms of energy and energy transfer? What branch of physics is that? Alright, hopefully you said thermodynamics. Now there's two parts to thermodynamics. What do you call the matter or portion of the universe that is currently being studied? Alright, that system. What do you call everything else? And technically it's everything else in the entire universe besides whatever it is you're studying. But in all practical circumstances, it's literally the rest of the room typically. Alright, great, so the surroundings. Okay, let's see. Who was the first person to clearly state the first law of thermodynamics? Now again, this guy wasn't in bold, but you should still know him. So we're not just going over just the bold terms. You're going over the italicized terms too as well. But you only need to copy the bold terms. so Julius Robert von Meyer. So make a note for his name if you didn't know it previously. Go ahead and write down his name so you can study his later. All right, who was the person that experimented with heating water and he discovered the mechanical equivalent of heat? Who's that guy? All right, hopefully you wrote down James Prescott Joule, so make a note for him. Now, mechanical equivalent of heat is bolded, but make sure that you note that he was the person that was discovering it. So don't just note that the relationship between mechanical energy and heat is called mechanical equivalent of heat. Make sure that you note that he was the person that discovered it. All right, what is the law, idea, or principle that states that the energy gained or lost by a system is equal to the energy gained or lost by its surroundings? So this is a law at this point, so it's not just the law of conservation of energy. This is a more better worded version of it. It's the first law of thermodynamics. Good job. So the first law of thermodynamics, make a note for that. This is just restating it. It's put better, and it's put nicer than just the law of conservation of energy. So just make a note for that. That states that the energy gained or lost by a system is equal to the energy gained or lost by its surroundings. All right, who is sometimes considered the founder of the science of thermodynamics? Alright, so again, his name was not in bold, but was in italics, and you know it. So Sadi Carnot, so make a note for him. So if you didn't remember him, you should write him down so we can study him later. What is a theoretical device that would generate the maximum amount of work from a given amount of heat? Saying, in theory, if I put 25 joules into something, of 25 joules of heat, I should get 25 joules of work out of it. Now again, that works in theory on paper, and in real life it doesn't work that way. But what do we call that theoretical device? Alright, it's a Carnot engine, so make a note for that. Alright, what do we call what is the law that states that natural processes tend to go one way towards less usable energy and greater disorder? So natural processes tend to increase disorder in a system. So stuff naturally wears out. What do we call that law? Good job, that's the second law of thermodynamics. So hopefully you knew that one. Alright, what do we measure the amount of disorder in a system? What do we use? What's the term that means the amount of disorder in a system? Entropy. Perfect. So make a note for that. Alright, so for the two people that are trying to watch this live, like I mentioned at the beginning of the video in case you missed it, that we are having a quiz today. So if you want to come away from this, that way you have a chance to study on your own before we come back and actually take the quiz, you can. Or if you just want to take it blind, okay, that also works as well. If you feel confident enough to go ahead and take it. So let's go ahead then and let's take out one piece of paper. You don't need a cover sheet because I'm assuming you are home alone or home with the parents and with siblings. So because of that, you only need one piece of paper, a pen, so that way you can go ahead and write down your answers for it. You don't need a cover sheet, you don't need a pencil, but you do need a working pen and a piece of paper. So go ahead and do that. So if you need to go get something, pause the video and then come back to it. Alright, make sure you write your name and the date at the top. You can just write science quiz or physical science quiz. I will figure out which number this is, and that's not a problem. But just make sure you write your name at the top so whenever I print them all, I can tell whose is whose. So write your name and write the date at the top for it. Number 1 through 10. Alright, number 1. What do you call the process by which heat flows through materials and between objects in direct contact? What type of heat transfer is that? So what's the process by which heat flows through materials and between objects in direct contact? What is that? Number 2, what is the type of heat transfer to where it can go through the vacuum of space? So this is the transfer of light energy, so that helps you out. Just make sure that this one is the only one where it can transfer its energy without matter. So what type of heat transfer is that? Number 3, what do you call the type of thermoses that are used to store liquid oxygen, liquid hydrogen, or liquid gases? They typically store really, really, really cold objects. Sometimes really hot, but typically really cold. What do you call that type of thermos? Right, number 4, what is the branch of physics that deals with thermal energy, heat, and their relationships to other forms of energy and energy transfer? What do you call the branch of physics that deals with thermal energy, heat, and their relationships to other forms of energy and energy transfer? What do you call that branch of physics? Alright, whenever you're working with that branch of physics, what do you call the matter or portion of the universe being studied? So, whenever you are working with that branch of physics, what do we call the quarter or matter of the universe the portion or the matter of the universe that are being studied. What do we call that? What you're actually working with. All right, number 6. Who discovered the mechanical equivalent of heat? He was working with water with weights. So who discovered the mechanical equivalent of heat? Remember, you want to get first and last name, but if you can't remember this guy's first name, you need to at least give me his last name. All right, number 7. What is the law that states that the energy gained or lost by a system is equal to the energy gained or lost by its surroundings? So what is the law that states that the energy gained or lost by a system is equal to the energy gained or lost by its surroundings? So what do we call that law? You want to give the exact name for it as best you can. All right, number 8. Who is sometimes considered the founder of the science of thermodynamics? Who is sometimes considered the founder of the science of thermodynamics? Number 9, what is a theoretical device that would generate the maximum amount of work from a given amount of heat? So what do you call that device to where, in theory, if you were to put in 25 joules of heat, you would get 25 joules of work out of it? So what is that? So what is that theoretical device? In real life, it doesn't work this way, but in theory, it should. And then number 10, what is the term that refers to the measure to the amount of disorder in the system? Number 10, what do you call the measure of the amount of disorder in the system? What term do you refer to that disorder in it? Alright, so if you need to go back, because I went through one of the questions too fast because I can't tell if anyone needs anything repeated, you can go back and rewind the video and play back that individual question. But hopefully you got them all and you wrote down all your answers, so go ahead and put that off to the side, so that way you can give it to your parents later, so that way they can take a picture of it, so that way they can email it to me later. So just keep it off to the side, so that way you can give it to them later and ask them to take a photo of it, so they can email it to me later on today. But hopefully you did really well on it. Alright, so let's go ahead and let's open up your textbooks and turn over to page number 100. I guess we're on page 99, technically is where we left off last. So heat and changes of state. So we talked about how there's 3 ordinary states of matter on Earth. So there's a solid, liquid, and gas. Plasma is there as well, but typically we don't count that one too much on a day-to-day basis. So there are 3 common or ordinary states of matter on Earth. So solid, liquid, and gas. We talked about the kinetic theory of matter already. So when we talk about the energy of a solid, liquid, or gas, which one has the most kinetic energy? Well, hopefully you said, okay, gas, because that one has the most energy because the molecules are breaking away. If we're talking about which state of matter has the least kinetic energy, which one has the least kinetic energy? Solid. Good job for that. Alright, so I'm going to go ahead and shift this over so you can see this one. I started showing this picture on Friday, but then we ran out of time. Alright, melting and freezing. So your book points out, okay, if we're having state changes, we're having an object go from a solid to a liquid or a liquid to a solid, that is a state change or a change in the properties of the object. So the changing from a solid to a liquid is melting. So if you're going from the solid form to the liquid form, that is melting. Typically we associate it with water. That's the major one for it. There's other things though as well. So if I have a bar of iron and I apply a lot of heat to it, either with a blowtorch or something else, and I keep adding heat into it, eventually my iron will start to melt into molten iron. So it's the same idea. We just associate it with water because water we work with on a day-to-day basis. Just because this is changing from a solid into a liquid is just melting or fusion. That's another term for it. So melting's fine. Just make a note that the fusion is the other term for it. So the changing of a solid to a liquid is melting or fusing. The temperature at which the melting occurs is the melting point. Like for water, the melting point, if you have ice and I let it sit out in the sun, the point where it melts is at 0 degrees Celsius. That's whenever it starts to melt and turn back into liquid. Now the changing from a liquid into a solid, if you're going from liquid water into solid water, that is freezing. I know this feels really basic right now, but your book's just making sure that you understand. The temperature at which this occurs is the freezing point. So if I'm going from a liquid water and I'm taking heat out of it and I put it in the freezer and I leave it overnight, the temperature at when my liquid cup of water turns into a solid cup of water, that happens at 0 degrees Celsius. Now you might think, well, it's the same temperature. Yeah, it is. So it depends on which direction your substance is going. Are you putting heat into it or are you taking heat out of it? So it actually goes either direction. It just depends on, are you putting heat in or are you putting heat out for it? All right, so your book talks about freezing point depression really quick, and we'll come back to talking about this idea as well. So if I want to lower the freezing point of, say, water, I can do it a couple different ways. One of the ways is I can add in a solute. A solute is a substance that dissolves in a liquid. This is called freezing point depression. This is whenever I am lowering the freezing point of water. I am making it to where water has to get to a colder temperature in order for it to freeze. Now again, this works with other substances. We just use water more. This will come, I keep referencing water. So I put in a solute. A solute is a substance that dissolves into a liquid. So this one is called, it's called freezing point depression. For example, your book points out that we can put antifreeze into water to lower its freezing point. We also use, in some cases, like if it ever snows or if you get ice over here in Georgia, that typically, depending on where you're at, they might throw salt on the sidewalk or salt on the road. So if you're up north, they might use salt more. But since we're in Georgia and we don't have a lot of salt, we have to use something else. Typically over here, I see people use sand. So sand does the same thing as salt does. But if you take sand and if you throw it on the ice, it kind of gets in the way of the ice molecules and it helps it to break apart or start to melt, so it melts them faster. So just make a note though that we call this freezing point depression. Now you might think, well, why does this work? Well, if I have a cup of water molecules and it's full of water molecules on the inside, if I add in a solute or a substance that dissolves on the inside of it, basically it clutters it up so that way the water molecules, they can't bind and lock onto each other to form a solid chunk of ice. That those solutes get in the way and clutter it up. So that's how come they have to take out a lot more energy for the water molecules to get around them so that way now they can lock into their placement for it. So your book points out, well, salt also lowers the freezing point of water. Antifreeze is used in cars so that way the water in the engine doesn't freeze. That's the reason why if you live up north, they might use salt, but down here in Georgia, they use sand because we just don't have a lot of salt apparently. And sand is easier for us to use. So make a note that that's called freezing point depression. So you're lowering the freezing point. So make a note for that one. All right, latent heat. So your book points out that once you have the solid reach its melting point, that its temperature will not change until the solid has melted. So if you're looking at this diagram on your book points out that, okay, if I have 1 gram of water at 0 degrees Celsius or 1 gram of ice at 0 degrees Celsius. Now keep in mind, water will either freeze at 0 degrees or the ice will melt at 0 degrees Celsius. It just depends on if I'm putting energy in or taking energy out. If I'm taking energy out, what do we use? What sign? A positive sign or a negative sign? You're taking energy out of your system. Right, you take it out, so we use it as a negative sign, like you're using it for money or finances. What if I'm putting heat into it? Right, that's a positive sign. So, if I have 1 gram of water at 0 degrees Celsius, I have to take energy out if I want it to freeze. If I have 1 gram of ice at 0 degrees Celsius, I have to put energy into it in order for it to melt. So it's kind of like going, it's kind of like using a door, if you want to think of it this way. If the door represents 0 degrees Celsius, to go, I can only go through a door typically 2 ways. And I'm sure a couple of you could get really creative and go through a door in a couple different ways. But typically you either go through a door from like the classroom out to the hallway, or from the hallway into my classroom. There are 2 basic ways you have to go through the door. So that's the idea. So if I'm going from my classroom into the hallway, you might be saying, okay, I'm leaving. So that is negative. So I'm going out that direction. If you're coming into my classroom, you're gaining, you're coming into the classroom. So you can use that as a positive sign. So that's kind of helps you to kind of associate what's happening with the water because it just depends on what direction that you're going. Are you gaining heat or are you losing heat? Now, if I have this 1 gram of ice and I have to melt it, I have to give it enough energy for it to break apart. Because remember, with cohesion, those molecules are locked into place. So I have to be able to give it enough energy to have those molecules break apart. We call that latent heat. If you want to think of it kind of like hidden. Latent refers to something that is present but not visible. So if you were to hold up a thermometer to this 1 gram chunk of ice, it would constantly show up 0 degrees Celsius. Even though you might be actively adding in 334 joules of heat, it's not going to show its temperature change because that temperature, that energy, is not being used to it's not being used to change the temperature. It's being used to break apart those bonds on the inside of the ice. That's why it's considered latent or hidden heat, because it's there, it's being used, it's just not showing up in the temperature change. So if I want to melt this gram of ice, I have to add in 334 joules of heat for just this 1 gram of ice to melt. Now if I want this 1 gram of ice to freeze, then I have to take out of it 334 joules of energy in order for it to freeze. So the numbers are the exact same too. You'll notice, oh, this is the exact same idea. Yep, it is. So we call this latent heat required to change a given mass of a solid into a liquid without changing its temperature. It's called heat of fusion. So if I want to go one direction with the water and I need it to freeze, then I have to take out or remove 334 joules of heat. So that way the water molecules, since they have energy as a liquid, I have to take out that much energy for them to lose enough energy for them to lock into place so they are a solid. So that's the heat of fusion, or the latent heat for water, to where that heat's of fusion where I have to take out that much energy. Now once I have it frozen, if I want to melt that gram of ice now, I have to add back in 334 joules of heat. That's whenever I give them enough energy now to where they have enough energy to be able to break apart from each other and to turn back into that liquid flowing stage. So same idea as with the reference point for like 0 degrees Celsius as the freezing point or melting point. It just depends on what direction you're going. Same idea, to where if you're putting heat in, they're gaining it. So it's positive 334. If you're taking heat out, it's negative 334 joules because you're taking it out of it. Alright, you do not have to know the different melting points on page 100. Your book did list you a whole bunch of them. You don't have to know them, and you don't have to know the heats of fusion. Keep in mind, this is joules per gram. That's where your homework question came from, asking you, okay, instead of having just 1 gram of water, what if you have 30 grams? Okay, well, now, the one in your book was actually asking about iron. So if you look at that chart, you'll notice that iron has 247 joules per gram. So that's why it's 30 times 247. Because it's not just 1 gram that you're working with. You're working with 30 of them. So I have to add in for each gram the 247 joules. So that's why for these two, you have to multiply them together. So hopefully that makes sense now. Okay, that's pretty much everything with the latent heat. So let's go ahead and let's move on from that. So where it's just pointing out that, okay, that you won't notice the temperature change of your ice. So if you were looking at this container again, if you were to take the temperature of this glass, the average temperature for this one would be 0 degrees Celsius. Because all the heat on the inside that it's gaining is in the process of melting the ice cubes on the inside. Now once all the ice cubes have melted, now the temperature might start to increase if you were to let it sit out in the sunlight. But since if you're letting this cup just sit on a surface, that the temperature on the inside of the ice won't change because it's in the process of trying to melt these ice cubes first. Alright, so that's the idea of latent heat or heat of fusion. The heat required to give a mass of a solid to a liquid without changing its temperature. Okay, so that's pretty much it with the idea of freezing and melting. So now listen to evaporation and condensation. So your book points out, if you have a glass of water is poured onto a hot sidewalk, the water will disappear eventually. Okay, well why does it disappear? That's because the water is changing form into its gaseous form, or the next state. So it's changing into water vapor. This is the gaseous form of water. The change of a substance from a liquid into a gas is called evaporation. Sometimes you see your vaporization. Okay, that's another term for it, but evaporation, that is the term that you want to know for it. So evaporation, vaporization is another name for it, but evaporation. Alright, there's a couple of different properties to exist, factors that affecting evaporation. So your book has this chart at the top of page 101. So if you want to mark them as you're going through them, you can. Your book also talks about them as we're going through it as well. So temperature. Alright, so factors affecting evaporation. So if it's a hotter day outside, the sunlight is giving more energy to your puddle of water or your swimming pool or wherever the liquid is located. And so because of that, it'll start to evaporate faster because it's getting more energy from the sun. So temperature, that affects it. The hotter it is around it, the faster you'll have the object or the liquid start to evaporate. So that would make sense for it. The next one is the amount of surface area. You might have noticed that car washes and other places that they try to spread out the water as much as possible with kind of like those, looks like rubber mops, where they're trying to spread out the liquid all around the concrete. And you might have wondered, well, why are they doing it that way? Wouldn't they want the puddles to stay in one area? No, because if you have a thinner puddle, it evaporates faster. So if you take a large amount of water and spread it out to where it's as flat as possible, you're increasing the surface area. So if you have a large amount of surface area, that's more area for the sunlight to strike the top of the liquid and start to evaporate it off faster. So you can think of it, you might have had like a puddle, maybe once your parents have washed the car, and your parents might have tried to spread out the water. So the reason why is that if you have a thick, deep puddle, or if you have it spread out over a large area, the sunlight, as the sun is giving energy, the sun can strike more area of the large flat puddle as opposed to the thicker puddle. And so that's why this one will evaporate faster. And so that's the goal of a lot of cases for puddles, in particular why your parents want to get rid of them, or if they're trying to get rid of them. That's the reason why. They're trying to increase the amount of surface area. The thinner it is, the more you can have the sun beating down on it and it cause it to evaporate. Strength of air currents above it. So if you're at an area and it's a very windy day, the wind is blowing over the top of the water. And so the wind is a type of energy, and so the wind is causing the water molecules to move. And so because of that, the wind can be giving it enough energy to cause it to come off and to evaporate that way. You use this typically as a lady, as a gentleman, you might use it as well. But you can use it if you're blow drying your hair. Typically you turn on the blow dryer to the highest setting, the fastest setting, because it's blowing faster and it'll evaporate your hair and dry it out a lot quicker. Now gentlemen, you may also use a blow dryer because your hair is shorter and you just need to hurry up and dry as quickly as possible. That's more of a young lady thing, to where young ladies have longer or thicker hair and they need it to evaporate quickly, so they need to put as much air through it as possible. This also works with hand dryers. If you've ever used a hand dryer at a restaurant or at a gas station or somewhere where you're using a public bathroom, you'll notice they have those hand dryers that you stick your hands under or in for them to dry, which I don't like the in ones as a personal note. Whenever you stick your hands on the inside, it just creeps me out and I don't like it. But that's part of the reason as to why typically they blow very powerfully, is they're trying to dry the water off your hands, and they're focusing on using the air currents, the strength of them. The faster the air is moving, the more energy it can transfer to the liquid, and it can dry it off that way. You can also have air pressure as well for it. So the air pressure above the surface of a liquid, that can also cause it to evaporate quickly. We're going to talk more about this a little bit later on, but evaporation occurs whenever the water molecules have enough energy to overcome air pressure. So we've talked about this previously in regards to air pressure, which hopefully you remember what's the device to measure air pressure. So thinking back to it, because your exam is kind of coming up, what is the device that's used to measure air pressure? Well, hopefully you said barometer. And who was the person that discovered air pressure, that invented the barometer? Right, Torricelli. So just make sure that you still are thinking over them and that you're paying attention, so that way you still are kind of going back and rethinking about them, so that way you will be ready for your exam coming up. Alright, so getting into it, still focusing on this one. So if you have an object where there's air pressure above a liquid, to have the molecules evaporate, because remember, if you have, this is not going to be a good container. So if I have a container and it's full of liquid, my liquid escaped. You can still see it. I'll shift it over slightly. Not the best looking container, but it'll work. Alright, so air pressure is constantly pushing down on it. So the air molecules, if they're going to have enough energy to escape and turn into a gas in the air, they have to have enough energy to overcome that. We call that boiling, so we'll talk about that in a little bit later on. But that's the reason why air pressure affects them. So if you go to the Dead Sea where there's more air pressure, then that means that you're going to have to increase it to a higher temperature because it has to overcome more of the pressure. If you were to go up to the top of Mount Everest, ignoring the fact that it's really cold, and you were trying to boil the pot of water, which is very cold at the top of Mount Everest, and it wouldn't work properly. We're just going to focus on air pressure. But if you were to take your cup up to the top of Mount Everest and boil it, it would boil at a much lower temperature because there's less air pushing down on it. So again, we'll talk more about this with pressure cookers a little bit later on, but that's the idea of air pressure above the surface of a liquid. Sometimes some liquids are just more volatile or non-volatile. That's what's talking about with the properties of the liquid. Some liquids just boil at a lower temperature. So some liquids, they evaporate much more rapidly than others do underneath the same conditions. Liquids that evaporate quickly are volatile, while liquids that evaporate slowly are non-volatile. So sometimes just the property of the liquid makes it to where it wants to evaporate faster than other substances, and that's just parts of the liquid. So just make a note that volatile, that's a substance that evaporates quickly. Non-volatile, if it has a tendency to not evaporate all that quickly. Your book gives you a couple of examples. You don't have to note the examples, but your book is pointing out that gasoline, paint, thinner, these are examples of volatile liquids, while lubricating oil is an example of a non-volatile liquid. So just make a note for that. Alright, you want to make a note of these 5 things as the factors that affect evaporation, or factors affecting evaporation. That's kind of a mouthful. These are the 5 things. So just make note of them. So your book has a chart for page 101. I just put it in a condensed version like this. So either way works for it. So your book gives you an example of talking about, again, with blow drying your hair. So again, if you have your blow dryer set to a higher temperature, okay, that's why it'll dry your hair faster. You also want to be careful, ladies. You don't want to cook your hair. So if you cook it on the high setting all the time, you might have a tendency to burn your hair or to treat your hair unhealthily. Just be careful for that. Mass surface area. Also your book gives you the example of brushing your hair while you blow dry it or running your fingers through it. You're trying to increase the surface area. So that's another reason why you do that. Strength of air current, you turn on the highest setting with the air, so that way it blows as forcefully through your hair as possible. Now, typically if you're blow drying your hair, air pressure doesn't really affect it, and the property of water doesn't really affect it. But sometimes if you have conditioner in your hair or other gels, it'll make it dry slower. So that's the idea behind it. Alright, so boiling now. If you're going from a liquid to a gas, you are going from a liquid form into a gaseous form. We call that the boiling point. So like this pot in the example is at its boiling point. The liquid is going into the gaseous stage. So whenever you have evaporation occurring throughout the whole liquid, we say the whole pot is boiling. Sometimes if you've ever watched a pot, which you know a watched pot never boils, which is an old expression. It just means that if you watch it, it feels like it's taking forever. It will eventually boil. If you stand there and stare at a pot, it won't not boil because you're looking at it. That's just expression. It just means that it'll take forever or feel like it's taking forever if you stand there and watch it. But if you ever try to watch a pot boil, you'll notice that typically there's maybe a couple bubbles that escape out the top first. But we don't say it's actually boiling till you have bubbles throughout the whole container. So that's whenever all of the liquid is boiling at that point, not just the top layers just escaping. So, when evaporation occurs throughout the entire liquid, that's whenever we say it has begun to boil. This is whenever it reaches boiling point. Now, for water, what is water's boiling point in degrees Celsius? You probably have already learned this previously. Right, 100 degrees Celsius. So that's whenever it has reached its boiling point for water. That's whenever all of it will start to boil. Now, your book points out again that if you were to increase the temperature on your stove at this point to try to raise the temperature of the water, it won't go any higher. That's because, kind of like we're talking about, wrong direction, kind of talking about the latent heat of water going from a liquid to a solid, and it won't change anymore until all of it has changed from one state to another. The same idea is still here. Wrong direction. The same idea is still here. That until all of the water has evaporated out, the temperature of the water will not change. So you're just wasting energy with your house at that point, because the temperature of your water is not changing at that point. It's going to stay at 100 degrees Celsius. There's a couple of other things, though, you can do in order to increase the temperature of the water, because it's the temperature that cooks your food, how fast it cooks it. There's a couple of other things you can change instead if you want your food to cook faster, but if the temperature of the water won't change. So your book points out one of the ways we can do that is with increasing the pressure on a container. Your book talks about a pressure cooker. We will come back and talk about a pressure cooker tomorrow. But that's one reason you can actually increase the pressure on the inside of a pot, that you can increase the pressure, and that'll keep the water from boiling. So trying to draw this quickly because I'm not a good drawer. Okay, that's a decent pot. Alright, so if I have my liquid and it starts to boil, now keep in mind, if this is at standard atmospheric pressure, this will be at 100 degrees Celsius. So the air pressure, that's whenever you have the air pressure pushing down on it. And this is at normal atmospheric pressure. The air is pushing on it. But at 100 degrees Celsius, that's whenever the water has enough energy now to boil and to come out into the gaseous form. That's whenever it has enough energy, it's strong enough to come out from the liquid phase into the gaseous phase. Well, let's say I increase the pressure. Let's say I go down to the Dead Sea, which my geography people, which I'm pointing at empty room, so geography people, hopefully you remember that Dead Sea is the lowest point on Earth. The air pressure is stronger there. So the water would have to increase its temperature to a higher amount. It would have to have more energy for it to boil out at that point. And so that's the reason why a pressure cooker, it basically increases the pressure on the object. So that way it can boil at a higher temperature and cook your food faster. That's what your mom might use a pressure cooker for chili or soups or other types of food that typically takes a long time. She can do it at a much faster setting because at a much faster time, because it has it set to a higher setting. We'll come back and we'll talk about this later. I'm just about out of time. Since I gave you classwork, I'm going to go ahead and stop so that way you're not working on this too long. Alright, your homework for tonight. Go ahead and finish reading pages 102 through pages 104. So 102 through 104. Answer on page 110, 111. Question 6, and think number 1. So read pages 102 through 104. Answer on page 110 and 111. So it's going to go over from one page to the other. It's in the section review, the 5.4 section. So it's question 6 and think number 1. Don't forget the second draft of your background paper is still due Wednesday. We'll talk about how we're going to do it tomorrow. Just make a note that it is due Wednesday still. So if you haven't started working on it, you need to work on it. Alright, I hope you all have a great day, and I won't see you tomorrow, but you will see me.